Welcome all to today's lecture. The lecture series I am covering is for the subject VLSI Technology. Code is KEC053. The target students are the semester 5 students from Electronics and Communication branch. Today the topic that I'll cover is NMOS and CMOS fabrication sequence. Let's start with the fabrication of NMOS. As we all know that there are the various fabrication steps starting from the preparation of a die up to the testing. So initially when we are ready with the substrate. Now how will we fabricate NMOS? So first of all, on the raw substrate, the very first layer that is to be deposited is oxide layer, that is silicon dioxide. Since this is silicon substrate, this layer is silicon dioxide. That is the oxidation process. There are various different processes to do oxidation on silicon substrate. So using any of those processes, the oxide layer is drawn on silicon substrate. Next step is coat the silicon with photoresist. Now, when we are going to fabricate NMOS, what type of structure will this will look like? So suppose this is substrate and this is the P substrate, these are the N wells. So this is how the final product should look like. Okay, so we have to make two N wells inside this substrate to fabricate NMOS. So now this is the substrate. On the silicon substrate, I have to pattern these two wells, N wells. In order to pattern any structure in the substrate, the very first thing we do is patterning. For patterning, we require to deposit photoresist layer. So here in this step, what I am doing is, I am depositing photoresist. Okay, so this is oxide layer. This is substrate. This is photoresist. So let us now see the next step. As we all know, there are two types of photoresist. One is positive, one is negative. In case of positive photoresist, what happens is the portions of photoresist which are exposed to UV radiations or whatever the source we are using for exposure. So the portion which is exposed to UV light, that will become more soluble in the solvent. And when we are using negative photoresist, in that case, the portions which are exposed to UV lights, they will get hardened on exposure. So in this case, we are using positive photoresist. So here you can see this is the mask. So here we are using glass mask. So according to the portion, so as I've shown earlier, that here what you have to work with this portion, okay? So in this case, what will you do? You have to remove this portion, okay, to make gates and two wells. So you have to remove this portion, and to remove this portion, the photoresist layer is exposed to ultraviolet rays through the mask. This is a mask, and this mask has been fabricated in such a way that this portion is exposed to, through this portion, the photoresist is exposed to UV light. So when the photoresist is exposed to UV light in this particular portion, then this portion gets more soluble after exposure. Now, to remove this portion, what we are doing is, we are etching the substance. So we can prefer chemical etch, that is hydrofluoric acid etch, or we can prefer dry etching, that is a plasma etching. These are the two different processes having different properties and having different capabilities. So accordingly we can decide which type of etching we have to use. After etching, the photoresist from this particular portion has been removed, as we can see, and the remaining photoresist, this is a photoresist, the remaining photoresist has been hardened because it was not exposed to UV light. So now we can see the final structure. Here is the SiO2 layer. This is SiO2 layer. And on this SiO2 layer, this particular portion is exposed is exposed, and this portion can be used to deposit other component devices or to make other devices, we can see. So this photoresist layer has been hardened. So now the SiO2 regions which are not covered by hardened photoresist can be etched away either by etching. Finally, what we are getting, the photoresist portion, the photoresist layers on other portions is also being etched. So you can see there is no more photoresist found. So now the remaining photoresist can be removed by using another solvent. So from all of the surface, the photoresist has been removed. Now deposit a layer of thin oxide in order to form gate oxide of the NMOS transistor. Now what we have to do, we have to fabricate the gate. And for fabrication of gate, we have already aware of this fact that a thin oxide layer, that is a film deposition, has to be done. This can be thin oxide. So again, through the thin film deposition process, a thin oxide is grown all over the surface, all over SiO2 oxide. Now on the top of thin oxide layer, a layer of polysilicon is deposited. As we can see, this was SiO2 thick oxide layer. Through patterning, the thick oxide layer has been removed from this portion. Now this is a thin film of oxide layer, thin oxide. Again above the thin oxide, this is the polysilicon. And this polysilicon layer is used to make interconnects, to form the metallization. So now on the top of thin oxide, a layer of polysilicon is deposited. It is used as gate electrode material for MOS to interconnect it. So basically this polysilicon is used for making the gate electrode. Now through etching, we have to define the gate over here. So all the portions of thin polysilicon layer except this portion is removed through etching. So this is the final result. As we can see, in this particular portion where the gate has to be defined, we are left with polysilicon layer. Rest from all other portions, the polysilicon has been removed. So now this is the final structure. This is thick oxide, this is thin oxide, this is the thin polysilicon layer. Only in this portion, because the gate electrode has to be defined only in this particular portion. Now, next, the thin oxide not covered by polysilicon is also etched away. So as we can see, the oxide from this portion is also removed. Here, the oxide has been removed from these portions. So the source and the drain junctions can be formed. So here the source and the drain have to be formed. For this, the thin silicon oxide layer has been removed, has been etched. Now, through diffusion process or ion implantation, we can define these two, source and drains, for NMOS device. The entire silicon surface is then doped with a high concentration of impurities, either by diffusion or ion implantation. So in this way, first of all, we are able to define these two source and drain regions in NMOS. And since this is NMOS device, so these two wells, these two regions are N-type and the substrate is P-type. So in this process, what we now, so starting from the mere substrate, p-type substrate, we are now done with the two source and drain regions. Now what will be the next step? Next step is to make the interconnections of these regions. Once the source and drain regions are completed, the entire surface is again covered with insulating layer of SiO2 to form the interconnections. So here we can see after the achievement of these two devices, these two areas, again insulating layer, that is the oxide layer, is again grown all over the surface. So we can see here is the layer grown again. The insulating oxide is then patterned in order to provide the contact window for drain and source junctions. So here you have to open the contact windows. So for opening the contact window, what we are doing? We are etching the oxide layers from these two regions. This is the insulating oxide. Now the surface is now covered with evaporated aluminium, which will be used for making the interconnections. Now after this step, what we are going to do? We are going to cover this whole portion using the metal layer. So here this is the metal layer, and it is covering the all over surface. Now we have to make the openings for gate, source and drain. Finally, the metal layer is patterned and etched, completing the interconnections of the MOS transistor on the surface. So in this way, to make the interconnections, only these areas are used to make the interconnections. So this is the metal contacts can be seen only in these regions. So this is how the final product looks like. Let us again give a quick recap. So starting from the substrate, then first of all the oxide layer was grown, and then the polysilicon layer was deposited. Then it was patterned to make the openings for source, drain and the gate regions. Now again the etching was done and the thin oxide layer was grown. On the thin oxide layer, again the polysilicon layer was grown to make the interconnections. And then it was used to form the gate. So to make the gates, the oxide layer from the other regions are also removed. Now again, here through these openings, source and drain regions are defined. After defining the source and drain regions, again the insulating oxide layer is grown in order to make the metallic contacts. After this oxide layer is grown, it is etched from these particular areas where the metallization has to be done. And in the final step, the metallic layer is deposited and again etched to give the external connections to these areas, source and drain. So this was a whole process of NMOS. Similarly, there is a complete process for CMOS, and we are well aware that in CMOS, we are going to define both NMOS and PMOS on the single substrate. So in this, again starting from the initial step, that is a growth of oxide layer on the p-type substrate. Again, in this area, we have to define the N-well in order to make PMOS. So we have to make PMOSFET in this area, and for this, we have to pattern this area. So the etching is done, etching of oxide layer is done from this particular area using the photolithography. So as shown in the NMOS, in the process, fabrication process, again the patterning is done through the mask. It must be using some mask, and here this area has been exposed to UV rays, and the exposed area becomes more soluble, and hence it can be etched in the final step. Now after the etching, the N-well is diffused. Okay, so in this the N-well is formed. Again, in this portion, we have to make PMOS. That is a PMOS. In this portion, we have to make N-MOSFET. So the N-MOSFET is grown in the p-type substrate itself. So no need to make another well. So using the patterning and etching, again this area is formed and the oxide layer is grown all over the surface, a thin oxide layer. To make the gate electrodes, we have to deposit polysilicon all over the surface. So here you can see a green layer, that is denoting the polysilicon layer. Now we are done with the N-well. We are done with the polysilicon layer. Now we will make the gate electrodes in this portion. And hence the polysilicon and oxide layer from all other portions from this portion has to be removed. So we can see in the next step that the polysilicon layer and the oxide layer has been removed from these steps. And we are left with the polysilicon layer only in the gate electrode part. Now we can see, before defining the gate electrodes, before defining the gate terminal, we have to make the NMOS and PMOS over here. So we can see that in the N-well, the P-type diffusions are done to make the source and drain regions. And in the for fabrication of N-MOSFET, here the N-type diffusion is done. N-type devices are formed in the P-type substrate. In the next step, to fabricate the metallic layer, or we can say to do the metallization, before that we have to grow the nitride layer, silicon nitride. So we can see, after attaining this step, we have to deposit the metal all over the surface. So this is all the metallic layer. Sorry, this is all the nitride layer. So to make the metallic contacts over here, to make the metallic contacts in the source drain, so we have to do the metallization, and before doing metallization we have to grow the nitride layer. So this is the nitride layer. Again, using the patterning and etching, the nitride is removed from these portions, because here the metallic layers has to be grown. In the next step, after etching, the metallic layer is grown all over the surface. So this is all the metallic layer. Now after depositing the metal, we have to etch the metal in the desired locations. And what are the desired locations? So we have to leave the metallic layer only here, for the source areas, for defining the source interconnects, for defining the gate interconnects, and this is for drain connections. So apart from this source, drain and the gate, we have to remove the metallic layer. So we can see the metallic layer has been etched from all these portions. From all these portions. So we are left with this final product. So this final product is CMOS with two wells, with the two types of MOSFETs. That is this is the P MOSFET, this is N MOSFET. These are the source areas, this is the drain areas, and these are the gate electrodes. So let's give a quick recap to the fabrication process of CMOS. In the fabrication process of CMOS, we are again starting with the P-type substrate. So CMOS, here in this case, the CMOS is fabricated on the P-type substrate, starting with the deposition of oxide layer on the P-type substrate. And I have not shown this step between these two steps. Between these two steps, there is a process of photoresist deposition. A photoresist layer is deposited on the oxide layer, and after using the mask and patterning, the photoresist has been removed from the oxide layer has been removed from this portion, and in the final step the photoresist which has been deposited on the surface has been removed. So now we are left with the substrate, and we are having an open portion over here in which the N-type well has been created using diffusion process. Again, from again in the second patterning step, this portion has been exposed and the oxide layer has been etched, which is used for making the N MOSFET. Again, after depositing the gate oxide layer and polysilicon layer, etching is done to make the gate electrodes, and after fabricating the gate electrodes, finally the diffusion process is used, or ion implantation used, to create the source and drain regions in both P MOSFET and N MOSFET. After this, the nitride layer is grown before metallization, and after etching the nitride layer, the metallic layer is deposited all over the surface and etched to form the drain. This is the drain region to form the source, drain and gate regions to give the interconnections to these regions. So this was the complete process for CMOS fabrication. So in this lecture, we have covered both the NMOS and CMOS fabrication sequence, and so that was all for today's lecture. Thank you.